Title of the module: Maximal Ideals and Prime Ideals. Dear learners, in this session we introduce two special ideals, namely the maximal ideal and the prime ideal. These ideals are motivated in large part by certain arithmetic properties of integers. One important class of ideals is those which are not contained in any other proper ideal. Definition of an ideal: an ideal M in an arbitrary ring R is called a maximal ideal if M is not equal to S and the only ideals containing M are M and R. Example: the maximal ideals of Z are P, Z. Here P is a prime. Let R be equal to Z cross Z. Then R is a ring where addition and multiplication defined by A comma B plus C comma D equals A plus C comma B plus D, and A comma B dot C comma D is equal to AC comma BD for all A comma B C comma D belonging to R. These are ordered pairs. Let I be equal to Z cross singleton 0. Then I is not a maximal ideal of R, since I is a subset of Z cross 2Z, which is a subset of R. The ideal generated by x squared plus 1 is maximal in R of x. To see this, assume that J is an ideal of R of x that properly contains the ideal generated by x squared plus 1. We will prove that J equal to R of x by showing that J contains some non-zero real number C, and this is the constant polynomial h of x equals to C for all x. Then 1 is equal to 1 by C times C, which belongs to J, and therefore J equals R of x. To this end, let f of x belong to J, but f of x does not belong to the ideal generated by x squared plus 1. Then f of x is equal to q of x times x squared plus 1 plus or R of x, where R of x is not equal to 0 and the degree of R of x is less than 2. It follows that R of x is equal to Ax plus b, where A and b are not both 0, and Ax plus b equals R of x, which in turn equals f of x equal to q of x times x squared plus 1, which belongs to J. Thus, a squared x squared minus b squared equals Ax plus b times Ax minus b, which belongs to J, and a squared x squared plus 1, which belongs to J. So, 0 is not equal to a squared plus b squared, which is equal to a squared x squared plus a squared minus a squared x squared minus b squared, and this belongs to J. That is, J is equal to R. A general ring need not have maximal ideals. For example, consider the set of rational numbers Q and make it into a trivial ring by definition AB equals 0 for all A comma B. In such a ring, the ideals are simply the subgroups, and so there are no maximal ideals. The zero ring has no maximal ideals. Hence, any result involving maximal ideals forces a ring to be non-zero. The next theorem shows that the rings with an identity I not equal to 0 always possess maximal ideals. Like many such general existence theorems, and the proof is relied on Zorn's lemma. In many specific rings, however, the presence of maximal ideals is often obvious, independent of Zorn's lemma. In order to prove the upcoming results, we need to recall Zorn's lemma. The Zorn's lemma is: if S less than or equal to is a partially ordered set such that every chain C in S has an upper bound in S, then for every element x in S, there is a maximal element y in S with x less than or equal to y. Now the theorem is, in a ring with identity, every proper ideal is contained in a maximal ideal. The proof, let R be a ring with identity and let I be a proper ideal, so R cannot be the 0 ring, that is 1 not equal to 0. Let S be the set of all proper ideals of R which contain 1. Then S is non-empty, 1 belongs to S and is partially ordered by inclusion. If C is a chain in S, define J to be the union of all ideals in C. Then J is equal to union over A belonging to C of all A. We first show that J is an ideal. Certainly, J is non-empty because C is non-empty. Specifically, 0 belongs to J since 0 is in every ideal A. If A, B belongs to J, then there are ideals A, B belonging to C such that A belongs to capital A and B belongs to capital B. By definition of a chain, either capital A is a subset of capital B or capital B is a subset of capital A. In either case, A minus B belongs to J, so J is closed under subtraction. Since each capital A belongs to the chain C, this is a contradiction because each A is a proper ideal because each A is a proper ideal A belonging to C, which is a subset of S. So each chain has an upper bound in S. By Zorn's lemma, S has a maximal element which is therefore a maximal ideal containing I. Using the above theorem, let us see some results. The result is, let R be a commutative ring with 1, then R has a maximal ideal. Proof, in R, singleton 0 is a proper ideal. Hence, by the above theorem, there exists a maximal ideal M of R such that 0 is a subset of M. The next result shows that every non-unit lies in a maximal ideal. The proof, if X is a non-unit element of the ring R, then the ideal generated by X is not equal to R. From the above theorem, we get the ideal generated by X contained in some maximal ideal M, that is, X belongs to M. For commutative rings, the next theorem characterizes maximal ideals by the structure of their quotient rings. Theorem, assume R is commutative. The ideal M is a maximal ideal if and only if the quotient ring R by M is a field. Proof, the ideal M is maximal if and only if there are no ideals I with M subset of I which is a subset of R. By the correspondence theorems for rings, the ideals of R containing M correspond bijectively with the ideals of R by M, so M is maximal if and only if the only ideals of R by M are 0 and M. By above proposition, we see that M is maximal if and only if R by M is a field. The above theorem indicates how to construct some fields which is nothing but to take the quotient of any commutative ring R with identity by a maximal ideal in R. Let us discuss some examples here. The quotient of the ring Z of X by maximal ideal generated by X plus 1 is a field. Let n be a non-negative integer. The ideal nZ of Z is a maximal ideal if and only if Z by nZ is a field. We have Z by Pz is a field, so Pz is a maximal ideal of Z. The ideal generated by X in Z of X by ideal generated by X is isomorphic to Z. Since the ideal generated by X in Z of X is the kernel of the surjective ring homomorphism from Z of X to Z given by evaluation at 0, since Z is not a field, we see again that the ideal generated by X is not a maximal ideal in Z of X. Now let us see some results here. Result, the following conditions on a commutative ring R with unity 1 not equal to 0 are equivalent. 1. R is a field. 2. R has no proper non-trivial ideal. And number 3. 0 is a maximal ideal in R. Proof: R is isomorphic to R by ideal generated by 0 and is a field if and only if the ideal generated by 0 is maximal. But clearly, the ideal generated by 0 is maximal if and only if R has no proper non-trivial ideals. Hence, the following conditions are equivalent. Next, we will see the definitions of another particular type of ideal called the prime ideal. The notation of a maximal ideal is fairly intuitive, but the definition of a prime ideal may seem a little strange. It is, however, a natural generalization of the notion of a prime in the integers z. The definition is: assume R is commutative. An ideal P is called a prime ideal if P is not equal to R and wherever the product AB of two elements is an element of P, then at least one of A and B is an element of P. Some examples of prime ideal are: the 0 ideal in any integral domain is prime since AB equals 0 if and only if A equals 0 or B equals 0. Let n be a non-negative integer. According to the above definition, the ideal nz is a prime ideal provided n is not equal to 1. If n is equal to 1, nz is not proper. And provided every time the product AB of two integers is an element of nz, at least one of A comma B is an element of z. If we put it in another way, if n not equal to 0, it must have the property that whenever n divides AB, n must divide A or divide B. This is equivalent to the usual definition that n is a prime number. Thus, the prime ideals of z are just the ideals Pz of z generated by prime numbers P together with the ideal 0. Note that for the integers z, there is no difference between the maximal ideals and the non-zero prime ideals. This is not true in general, but we shall see shortly that every maximal ideal is a prime ideal. First, we translate the notion of prime ideals into properties of quotient rings as we did for maximal ideals. Recall that an integral domain is a commutative ring with identity 1 not equal to 0 that has no 0 divisors. From the note, we know that prime and maximal ideals are not the same. Then let us verify that the quotient ring of R and P forms a field or not in the following theorem. Assume R is commutative, then the ideal P is a prime ideal in R if and only if the quotient ring R by P is an integral domain. The proof? This proof is simply a matter of translating the definition of a prime ideal into the language of quotients. The ideal P is a prime if and only if P is not equal to R and whenever AB belongs to P, then either A belongs to P or B belongs to P. Use the bar notation for elements of R by P, that is R bar is equal to R plus P. Note that R belongs to P if and only if the elements R bar is 0 in the quotient ring R by P. Thus, in the terminology of quotients, P is a prime ideal if and only if R is not equal to 0 and whenever A B bar is equal to A B bar is equal to 0 bar, then A bar is equal to 0 bar or B bar is equal to 0 bar, that is R by P is an integral domain. Note that a commutative ring with identity is an integral domain if and only if 0 is a prime ideal. Previously, we discussed that every maximal ideal is prime. Now, we will prove it here in this result. Assume R is commutative, every maximal ideal of R is a prime ideal. Proof? We have if M is a maximal ideal, then R by M is a field. A field is an integral domain, so the result follows from the above theorem. Note that in general, prime ideals need not be maximal ideals. For example, the ideal generated by x is a prime ideal in z of x. Since z of x by the ideal generated by x is equal to Z, this ideal is not a maximal ideal. The ideal generated by 0 is a prime ideal in Z of x, but it is not a maximal ideal. The principal ideals generated by primes in Z are both prime and maximal ideals. The zeroed ideal in Z is prime but not maximal. The next remark is, let X be a set and let R be a commutative ring and let F be the set of all functions from X to R. Let X belong to X, be a point of X, and let I be the ideal of all functions vanishing at X. Then F by I is isomorphic to R. Thus, I is prime if and only if R is an integral domain and I is maximal if and only if R is a field. Let us discuss some theorems of prime ideals. Theorem: let R be an integral domain. If every ideal of R is a prime ideal, then R is a field. Proof: let A not equal to 0 belong to R. Then A squared R is an ideal of R and hence it is a prime ideal. Now A squared belongs to A squared R. Since A squared R is a prime ideal, A belongs to A squared R. Thus, A is equal to A squared B for some B belonging to R. Then A times 1 minus AB is equal to 0. Since R is an integral domain and A is not equal to 0, 1 minus AB is equal to 0 and so AB equals 1. That is, A inverse is equal to B. So, every non-zero element A has an inverse in R, hence R is a field. Theorem: let R be a commutative ring and I be an ideal of R. Let P be a prime ideal of I. Then P is a prime ideal of R. Proof: let A belong to P be a subset of I and R belongs to R. Then RAR belongs to I. Therefore, A times RAR belongs to P and so AR the whole squared belongs to P. Since P is a prime ideal of I, AR belongs to P. Hence, P is an ideal of R. Theorem: a proper ideal I of ring R is maximal ideal if and only if for any ideal A of R, either A is a subset of I or A plus I equals R. Proof: suppose I is a maximal ideal of R and let A be any ideal of R. If A is not a subset of I, then A plus I is an ideal of R. Since I is maximal, A plus I equals R. Conversely, assume that the proper ideal I satisfies the given condition. Let J be an ideal of R such that I be a subset of J. Now, J is not a subset of I. From our conditions, we got I plus J equals R, but I plus J equals J. Thus, J is equal to R, hence I is a maximal ideal of R. The final result is let F be a field and let I be an ideal of a polynomial ring f of x. Then 1. I is maximal if and only if I is equal to the ideal generated by P of x for some irreducible polynomial P of x in f of x. Number 2. I is prime if and only if I is equal to the ideal generated by 0 or I is equal to the ideal generated by P of x for an irreducible P of x belonging to f of x. The table displayed on your screen shows ideals, prime ideals and maximal ideals of some standard rings. For the ring R, the ideals are 0 and R itself. The prime ideals are only singleton 0, the ideal generated by 0, and the maximal ideals are again the ideal generated by 0. For the ring Q, the ideal is the ideal generated by 0 and Q itself, but the prime ideals are the ideal generated by 0 only. The maximal ideal also is the same. For the ring Z, the ideals are NZ and the ring Z itself. The prime ideals are the ideal generated by 0 and a prime, so P Z. The maximal ideal is also P Z, where P is prime. For the ring Zn, where n is composite, the ideals are the ideal generated by 0 and the ideal generated by D, where D is a divisor of n for Zn, and Zn is also an ideal. For prime ideals in Zn, we have the ideal generated by P, where P divides n. The maximal ideal is also the ideal generated by P, where P divides n. For the ring Zp, where P is a prime number, the ideals are 0 and Zp. The prime ideals are 0 and the maximal ideal is also 0. For the ring Z cross Z, the ideals are Mz cross Nz, where M and N are inside Z. The prime ideals is the ideal generated by 0, 0, the ordered pair, as well as Pz cross Z and Z cross Pz. Also, the ideal generated by 0 cross Z and Z cross 0. So, these are the prime ideals of Z cross Z. The maximal ideals are Z cross Pz and Pz cross Z. In the ring f of x, where f is a field, the ideals are the ideal generated by 0 and the ideal generated by f of x. The prime ideals are the ideal generated by 0 and g of x, the ideal generated by g of x, where g of x is a non-constant irreducible. The maximal ideal is only the ideal generated by g of x. Conclusion. Dear learners, in this module we have studied about maximal and prime ideals. But before going to these two ideals, we first described about an ideal and we moved on to the maximal ideal and prime ideals. We also proved that the quotient ring R by M forms a field where M is maximal. In a similar manner, we also proved that R by P forms an integral domain where P is prime. We also discussed some important notes in which the commutative ring maximal ideals are always prime, but a prime need not be maximal all the time. We have finally concluded this session by identifying the maximal and prime ideals of some standard rings. I hope that this session was fruitful to you. Thank you.